Welcome to this presentation on the movement of quadruped robots. Here we will discuss our approach to make quadrupeds more efficient and robust in handling challenging local manipulation tasks. Quadruped robots provide a good balance between mobility and stability, so they can perform local manipulation tasks, for instance in offshore maintenance on platforms similar to that in the picture. To do these tasks, the robot has to withstand external forces such as disturbances, as well as gravity and the actual forces involved in manipulation. But the robot has limited motor torques, and the contact forces are limited by the friction cones, so it is hard to robustly perform these tasks. In this picture you see a person sitting down to help them to descend steep terrain. This same body-ground contact can also be useful for quadrupeds. For one, it can give more options for distributing friction forces. It also helps save motor torque because the body weight is supported directly. And finally, it frees up the legs to do other tasks, such as pushing objects. But body-ground contact is difficult to control. This is because the contact points between the body and the ground are unknown. Also, the legs cannot move freely when the belly touches the ground. So to maximize the potential of quadrupedal body-to-ground contact, we propose to use prongs, small legs rigidly attached to the body of the robot. The prongs solve the issues of control and manipulability, as the location of the contacts are known, but many questions remain. Today we will look into answering these first two questions: how effective are the prongs, and where we should put them to make them the most effective. The paper also explores the question of how to control the robot while using the prongs. We answer these questions in 3 steps. First, we look at the control theory aspect to explore the effect the prongs will have on the robot's robustness against disturbance forces. We present a metric for this robustness and propose some faster compute approximations. As the metric can also be used in other applications outside the prongs, we will compare the methods of approximating this metric in some detail. The second step is to use one of these approximations as an objective function to optimize the prong placement. This helps us to assess the value of the prongs. Finally, hardware experiments will show the prongs helping the robot to resist a push, and then show off the other benefits of the prongs, namely that they free up the other legs to perform manipulation. To determine how effective the prongs are, we look at the robot's ability to reject disturbance forces. To test the disturbance rejection ability, we use a metric which measures the magnitude of the smallest disturbance force that the robot cannot withstand without breaking motor limits, friction cone constraints, or deviating from the desired motion. This is known as the smallest unrejectable force, or SUF. This metric, or slight variations of, have been used in robotics research before. These 3 equations show the relationship between the disturbance force F, motor torques tau, and contact forces, lambda, as well as their constraints. The constraints are derived from the Newton-Euler equations, the motor torque limits, and the friction cones. We assume the robot's states and desired acceleration, denoted by q, and its time derivatives, are fixed. We see that all 3 relationships are linear in their unknown variables, f, tau, and lambda. This means that the set of their feasible combinations is a polytope. Here we see an example of such a polytope, where the y-axis represents the disturbances and the x-axis shows the available motor torques and contact forces. This polytope represents the set of forces that can be withstood using the available motor torques, and we use this to build our metric, the SUF. To build the SUF, we find all forces for which a feasible motor torque exists. You will recognize this as a projection. Normally, this would result in a 3-dimensional polytope in the space of the disturbance forces. From the remaining polytope, we can easily compute the boundary point nearest to the origin, for instance using linear programming. Unfortunately, directly computing this projection is too computationally expensive. Similar work in this area has found a sequence of polytope operations that results in the polytope of disturbance forces by using the sparse structure of the Jacobian, JF, and the invertibility of many of its submatrices. This method was then extended to disturbance forces at the end of the quadruped's limb in later work. The methods used in these papers are exact, but requires converting a vertex representation of the polytope to its half-space representation, which makes it slow to compute. Which is why we propose 4 approximations of the SUF, 2 based on linear programs, which we call the Fibonacci and single direction approaches. The 2 others are based on more general convex programming. We call these the Affine and the Quadratic methods. Let's explore these briefly. The Fibonacci approximation uses the idea that if we fix the direction of the contact force, the minimal magnitude of a non-rejectable force can be found with linear programming. By sampling along a grid of directions, called the Fibonacci sphere, we solve the linear programming problem at each of the sampled points, and combine them to approximate the feasible disturbance polytope, and then the SUF. The figure shows how the results are conservative under approximations of the feasible disturbance polytope and SUF. This technique can also be used in isolation to compute an inaccurate but fast approximation in a single direction. The single direction approximation in our comparison takes this approach and estimates the SUF using a disturbance in the direction of gravity. The other two approximations adapt an existing method to simultaneously approximate the projection and find the minimal unrejectable force. When applying these techniques to robotics, we see the projection step as a control problem, finding the optimal response, U, in terms of motor and contact forces for a given disturbance. The idea is to simultaneously optimize the control law and the worst case force direction, F hat, as to maximize the magnitude, rho, of all rejectable disturbance. The true optimal control law, which results in the projected polytope, cannot be found easily. But previous work shows that it's possible to find the optimal affine or quadratic control law via convex programming. The value of rho resulting from the programs is the approximation of the SUF. Now we've explored these approximations to find a rapid but accurate method of estimating the SUF, we now need to compare the computation speed and accuracy for each against the exact computation to see which is the most useful going forward. To do this, we sample random robot configurations from two scenarios. The first for manipulation, where the robot's four legs are on the ground and a manipulator is attached to the robot body, and the disturbance acts upon the end effector of the manipulator. This can be seen in the top left figure. The second is a teleoperation scenario, where three legs are on the ground and a force is acting upon the foot which is in the air. This can be seen in the bottom left figure. We see in the table on the top right that all approximations are much faster than the exact method, and the single direction approach is the fastest, followed by the affine method. In the bottom right, the accuracy of each method is shown. We normalized each approximation against the exact SUF for that configuration. So a value that is closer to 1 means a more accurate approximation. Values higher than 1 are undesirable. They overestimate the SUF, which can cause failure when executing motions. We see that the fast computation in the affine methods comes at the cost of accuracy. But for most applications, this amount of conservatism is acceptable. For the rest of the paper, we use this affine approximation methods to optimize the placement of the prongs. Now we've shown methods of quickly calculating SUF, which we use as a measure of robustness for a given configuration. We can investigate if adding prongs can improve robustness against disturbances over not using prongs. We now use the SUF to optimize prong placement. When optimizing prong placement, a manipulator is attached to the robot. The optimization objective is to maximize the SUF at the end effector. Due to the arm being attached at the front end of the robot, we place a prong near the front end. For symmetry, we place another prong the same distance from the back of the robot. For this reason, we also place the feet in a symmetric configuration. This setup leaves three parameters to be optimized: the height of the torso and the XY positions of the feet. Because the objective function is non-smooth, we use a gradient-free optimization method. What we see in the figure is the feasible force polytopes both with and without the prongs, with the inscribed sphere shown inside the polytope, whose radius represents the SUF. We see from this that the prongs mainly help resist forces that are aimed towards the prongs themselves. Looking a little deeper, we optimize the feet positions for every achievable torso height. We see that the prongs ensure that the robustness is high, even when the torso is not right next to the ground. When the torso position is very high from the ground, the prongs are less effective, but when the torso height is lower, the difference in robustness can be large, as much as 35%. Now we have properly optimized prongs, we move on to see how the prongs perform on the hardware. The controller we developed for these experiments is detailed in the paper, but not discussed here for brevity. On the hardware, we test the effect of the prongs, and the ability of our controller to use them effectively. To test this, we push the robot with a force sensor mounted on a rod. The results are shown here. The first two plots show the force of the push as measured by the force sensor, and the position of the torso over time. Together they show that the robot with and without prongs were pushed with similar forces, and the effective stiffness of the controller was the same in both cases. The bottom plot shows the torque output of one of the knee joints in the robot. We show that the robot indeed needs to use less torque to remain standing and resist the push by partially supporting its weight on the prongs. Even when pushed, it uses the prongs effectively, meaning there is a larger safety margin. Now we can look at the other benefits of the prongs: manipulation with the legs. These videos show some example behaviors, both clearing obstacles and lifting boxes. These motions are manually planned. though in future we would like to work on automating this planning process. This future planner would also decide whether or not to use prong contacts for a given task. It is likely that the affine approximation shown earlier can play a role in this. For an example of planning using the SUF as a performance metric, please take a look at another paper by Enrique Farello, also presented here at IROS. To conclude, here we saw how prongs can be used to enable useful body-to-ground contact. We discussed the approximation of the smallest unrejectable force, and showed that the affine approximation of this is useful for most situations. We also showed that using prongs can increase robustness by up to 35% as opposed to not using them. Finally, we showed that experiments with the robots using prongs to resist pushes and to free its legs to perform some basic manipulation tasks. Thank you for watching our presentation.